Okay, we've seen that torque is the cross product of the r vector with the f force vector. The net torque, of course, the r vector with the net force vector. Work is torque times angular displacement. Remember, torque is r times f, basically, and times delta theta. R delta theta is your delta s along the arc, so you're really multiplying force times delta s along the arc. And we saw that previously. A little more rigorously, tau is a vector and delta theta is a vector. Now the direction of delta theta, if I've got this strap rotating in a plane and I rotate it in this direction, take my right hand, put the fingers along here and rotate it in this direction, my thumb is pointing up. If this is the XY plane, my thumb is in the Z plane, it's in the positive Z plane. The counterclockwise rotation will correspond to a positive torque, okay? And if I'm going in the opposite direction, a little hard to do that, but here we got the, okay, thumbs down for the counterclockwise rotation. Negative torque, or negative delta theta. Okay, I said torque meant delta theta, but of course the torque, we've seen the direction of the torque is the direction of r cross the direction of f. In any case, a change in kinetic energy, of course, is equal to the work done by the net force in the case where the rotation is about a fixed axis, so that the strap, for example, is constrained to rotate about a fixed axle here, so it can't go moving off like this while it's also rotating, so it doesn't apply if I fling this thing, okay? That would not be rotation about a fixed axis. But if the axis is fixed, then it doesn't go anywhere. If it doesn't go anywhere, then there's no energy associated with motion in whatever direction that is, and the only energy is associated with the rotation. In that case, we can make this statement, okay? Net force times delta theta, and actually tau dot delta theta. But we're going to probably use this a little more. We just have to be careful about whether it's positive or negative. That's automatically taken care of if we use the vectors. That has its own complications. Okay, now let's consider an example. A small wheel of radius r, big wheel of radius big R. And we have a mass m suspended by a cord that's wrapped around this smaller wheel. Let's assume that we know the total moment of inertia of this system, and we'll talk about the total moment of inertia of this system in a minute. But we don't have a good way of calculating that yet, but we somehow know the total moment of inertia. And the mass m, the system's released, there's no friction. The mass descends through a displacement delta y. Okay, and actually delta y being a displacement is a vector, so I'm going to make that a vector. So the question is, what's the torque on the system? Now don't look at what I've just written. Stop, pause, think about the question, and see if you can answer the question. Okay, well, I assume you paused. Okay, well, this picture shows that small wheel with the force acting downward, and that could be the force of tension in the string, or it could be the force of gravity acting on the mass. They're not exactly the same because the mass is going to be accelerating downward. You have a small net force on the mass so that the tension and the gravitational forces are not equal and opposite as long as the mass is accelerating. So you got to watch that. In any case, you got a force F, and it's got a line of action here. So if that force is in fact exerted somewhere down here along the cord, wherever the mass is, we're still okay, because the line of action of this force passes through this, I've got my head in the way, the line of action of this force passes through this point. So I can use this as the r vector. Of course, I could let the r vector go from here to here, but I'm just going to let this be the r vector, or if you prefer, that could be taken to be the L vector, the moment arm, or the lever arm of the of the force. Okay. In any case, the torque is going to be R cross F. Now we're being a little bit loose about the signs of tau net and delta theta, but the R cross F, it's worth just stopping a minute to think about. The R is in this direction, the F is in this direction, so R cross F gives you a vector into the plane of the blackboard. So we got tau equals R cross F. If we take away the vectors, this R being perpendicular to the F force, we can just write tau equals RF, keeping in mind that we got to be a little careful about the sign. And what's F? F is just the force of gravity on this mass m, so F is just mg, so that the magnitude of the torque at least is R times mg. Now, how much work is done as we move through angle delta theta? Well, it's going to be mg times whatever delta theta is. Now the question is, what's delta theta? Well, we have a descent through displacement delta y. I'm just going to take the magnitude of that descent and get the arc distance through which the small wheel has to rotate. Well, if the cord descends, or if the mass descends through a distance delta y, how much cord has to unwrap from this wheel? Well, that's going to be delta y. The only way the mass can descend is if a corresponding amount of cord unwraps. And if the arc distance is delta y, then that means the wheel's going to have to rotate through a distance delta y, so that the delta theta is going to be the arc distance over the radius, which is magnitude of delta y over r. Delta y, again, being equal to the arc distance. It follows that the work done by the torque is tau delta theta, which is just tau being r times mg, delta theta being magnitude of delta y over r, and the work is mg times the magnitude of delta y. Now we also have the change in potential energy, the gravitational potential energy. What's that? Well, we know that that's just mg times delta y, so that delta y being a negative displacement and the force of gravity being in the direction of a negative displacement, the work done by gravity on the mass is positive. Since the mg vector and the delta y are in the same direction, that work is positive, but delta y is negative, so we could say that the work done, let me do this. Work done by gravity on the system is mg delta y, meaning mg times the magnitude of delta y, and I'm going to be redundant, just put the absolute value signs around this, so that the change in potential energy is negative mg times the magnitude of delta y, which would be mg times delta y without the vector sign over it. Okay, so in any case, what's going on here? We're losing gravitational potential energy. We're gaining rotational potential energy. Okay, we'll go on with this analysis in the next clip.